Hey, hi guys, welcome back to the channel. In this particular video, we're gonna cover audio processing for real-time speech recognition. This is gonna be a completely theoretical video. Once you complete this particular video, you will get a brief idea about audio processing and what steps we follow while doing audio processing for real-time speech recognition. This presentation explores the vital role of audio processing in real-time speech recognition. It's the foundation for conversational AI and voice assistants. The global ASR market is set to reach 27 billion by 2026. A key challenge is achieving sub minus 300 millisecond latency for natural interaction. Let's see what are the challenges and core concepts of real-time ASR. First is instant conversation. When you say a real-time speech recognition system, it should be as quick as possible. Let's take example of fingerprint recognition. It is too quick. So we have to build speech recognition like quick only. So for that, instant conversation is required. We have to convert spoken languages to text instantly. The second thing will be wide applications. This powers smart speakers and voice commands. And the third will latency goal. There is an aim for sub minus 300 millisecond latency for natural flows. The real-time ASR instantly converts speech to text. It faces challenges like noise and accents. And typically performance is measured by word error rate WER and real-time factor RTF. And RTF below 1 ensures real-time processing. Let's see the audio processing pipeline. First, input signal. Input signal starts with raw digital audio. After we get the input signal, we have to follow some core steps. Those core steps includes pre-emphasis, framing, and FFT, fast Fourier transform. The third step will be enhancements. Here we have to utilize VAD and noise reduction. The audio processing pipeline transforms raw audio into compact features. This prepares signal for acoustic models. In this, key step includes pre-emphasis and FFT. Enhancements like voice activity detection improves the clarity. So this was the audio processing pipeline usually used in speech recognition system. Let's see what is pre-emphasis and framing. Pre-emphasis boosts high frequencies in speech. This compensates for spectral slope. It also enhances format. On the other hand, framing divides audio into short and overlapping segments. This captures dynamic speech property. Typical frame size will be 20 to 30 milliseconds. Typical frame overlap will be 10 to 15 milliseconds. 25 milliseconds frame is equal to 400 samples in 16 kilohertz audio. Pre-emphasis enhances high frequency speech components. On the other hand, framing divides the signal into short overlapping segments. These steps are crucial for preparing audio data. They ensures accurate feature extraction. So this was the importance of pre-emphasis and framing. Let's see what is windowing and fast Fourier transform. Windowing function. Windowing function applies a mathematical window to each frame. It reduces spectral leakage and this smoothes frame edges. This will be mostly used in MFCC feature extraction. If you have followed my videos related to the MFCC feature extraction, you might have come across this word windowing. The second thing will be frequency conversion. Fast Fourier transform converts time domain frames to frequency spectrum. It reveals the dominant frequencies. Common FFT sizes are 512 or 1024 points. Windowing reduces spectral leakage by smoothing frame edges. On the other hand, fast Fourier transform converts frames to frequency spectra. This reveals the dominant frequencies in speech. Both the steps are essential for accurate analysis. Let's see the feature extraction with the help of male frequency septal coefficient MFCCs. On the left hand, you can see the graph for male frequency bank. Male frequency banks applies to power spectrum on a linear mil scale. This mimics human hearing sensitivity. Typically 20 to 40 filters are used. Second step will be discrete cosine transform. This helps to compress the filter bank output. It creates decolorated coefficients. Standard output is 12 to 13 MFCCs per frame. Third thing gonna be feature augmentation. MFCCs are augmented with energy. First and second derivatives are added. This results in 39 features. Male filter banks mimic human hearing sensitivity. The discrete cosine transform DCT compresses filter outputs. This yields MFCCs often augmented with energy and derivatives. This coefficient form a compact discriminative feature set. Let's see how we can reduce the noise and voice activated detection in audio processing. Noise reduction. Noise reduction nothing but surpasses unwanted background noise. All the technique includes spectral subtraction and deep learning. It improves ASR accuracy significantly in noisy environment. Second thing is voice activated detection. It identifies speech segments versus silence or noise. Algorithms range from energy-based to DNNs, reduces computational load by processing only relevant audio. So let's conclude this theory video and let's see what are the future directions for ASRs. First is end-to-end ASR. It's a direct mapping from raw data to text. Second is Edge AI. Edge AI increase on-device processing for privacy. And the third will be robustness. It will improve ASR in extreme noise. Robust audio processing is critical for accurate ASR. It enables natural human-computer interaction. Future trends includes end-to-end ASR for simpler pipelines. Edge AI will enhance privacy. Research continues to improve robustness in challenging environments. So that's it all for this particular video. I hope you have liked the video. This was the complete theory video. In further videos, I will introduce one end-to-end audio recognition system with the help of Python. So stay tuned for that. Make sure to like the video and subscribe to the channel for more such informative content. Thank you.